a bunch of people working. I told you my group is big. We have a center with many people, and those are the people that are working with us. And I have collaborators, as you can see, some of them in England, in Newcastle, and starting a new collaboration with interchange program with Thomas Gazenzer from Heidelberg, and hope that will work fine. Okay, so you see, there are many things we've been doing here, and people have been doing before. So just for localizing what I'm doing, in BEC, people study the vortices. Many people propose the turbulence based on the liquid helium experiments, and then a few groups start to see the signature of turbulence in the BEC, and then there are many possibilities: vortice type, wave type, and there are many groups doing in different ways. And one of the best way of investigating is going to the energy spectrum and seeing a power law type of behavior, which is an indication that, or at least is a signature that something is going differently there that wasn't before. And normally that's what we've been using to identify the type of turbulence we have. And people like Carlo and many others, Nazarenko, Tsubota, they've been calculating, depending on the type of turbulence we have, what kind of behavior in the energy spectrum we should have in a range of momentum. So, and there are classifications, and then there are other properties we can measure in a turbulent cloud, and I've been doing this. So we measure the expansion to see the behavior, because that should be like speckle of matter waves, right, propagating in space. Also, we've been measuring the integral scale length, and trying to measure the flux of particles going from low to high momentum. And all this has been somehow convinced us that we have a system that's turbulent, and how are the characteristics of the system we have. But then it seems that the turbulent cloud is a very good prototype for a study of quantum system far from equilibrium. And then we start a new set of experiments trying to identify if that's the case, and how can we investigate this contest of far from equilibrium system. So for a while we were characterizing the turbulent system. Now we are trying to understand how is the evolution of the system based on theories that are existent on the literature concerning the far from equilibrium quantum system. And we've been doing a few things that I'm going to show to you. First of all, maybe this is some of my slides will be very fast in the beginning, and then I will hold on the ones that are new. And we just published a paper on this non-thermal fixed points, which I would like to expand sometime. There are many types of turbulence that people have been studying, and I don't think that they fill it up the whole possibilities. But the most common studies are the ones that's called Kolmogorov type, which is bundle of vortices everywhere in your sample. And the behavior is exactly like a classical fluid with Kolmogorov type of law, obeying the cascade and everything. You have also the Vining, what they call super quantum, which is this tangle of vortices that for a long time we convinced ourselves that this was a kind of thing we have, because we observed at the very beginning the presence of vortices, and then we see nothing else besides big fluctuations. So we are convinced that this was the type of turbulence we have. And then, you know, there are the wave type of turbulence, which are not these topological defects, point defects like vortices, in your sample, but are more like elementary excitations, like the waves that you have. And those waves, they react and they produce this so-called wave turbulence. And basically, we've been trying to classify our system based on those informations. Okay, we have in the experimental part, two BECs that are dedicated to these studies. One is made of rubidium-87. Normally, we are dealing with condensates, which have about 1 million atoms and about a few times 10 to the 5th on the condensate itself. We work with fractions that goes from 30 to 90% of atoms in the condensate. And those are the rubidium atoms. And I'm not going to go in detail how to make condensates, because that will take a big part of the talk, and this is not what I want to discuss. But we do the conventional. In this case, is a fully magnetic trap. It's called the Yaffe-Pritchard type of configuration, and we produce a sample that's trapped in a harmonic cigar-shaped trap. But we do have another experiment that is sodium and potassium. And we've been studying now, here's where we've been trying to do the quenching. And we've been already verifying many aspects of it. We produce vortices, vortice lattice, and now we are quenching to see what kind of features we can observe. This experiment start with a magnet trap and then turn into a light trap. So we can manipulate potential much easier than we do with the magnet trap, because when you have a light trap, it's easier to manipulate intensities, and therefore you can manipulate the potential. So the whole thing is now how we excite, and we excite in the magnet trap. And now I'm going to speak mostly about the rubidium BEC, which basically we add the coils that allow to modify a little bit the potential, introducing rotations and deformations of the trap. We normally call shaking the condensate. And more recently, I adopted the atomic washing machine, because this is what we're doing. We're shaking in both directions, in all directions. And that, of course, introduce tiny rotations that can produce vortices and anti-vortices. And we let the system to evolve. And then we observe what's going on the system. And of course, the first thing we observe is the traditional scissor molds, which is evidence that we have a superfluid there and everything. The scissor mold is a bending mode of the cloud. It's lower frequency. And of course, when you excite your condensate, if you are very gentle, you excite molds like this instead of vortices and things like this. But the idea is to make vortices, so we shake a little harder, and here comes the vortices that are formed, and we've been able to produce a paper showing that they are made on the external part of the cloud and migrate in, more or less following the simulations that are done by Nicky Parker and many other authors, showing that actually vortices are generating on the edges and migrating in. And of course, we have to prove you have a vortice and anti-vortice. So we have done also a study showing that we can produce tripoles or just the triangular type of shape, showing that these stable configurations can only exist when we produce vortices and anti-vortices on our sample. We investigate for a while the growing of vortices as we excite with different amplitude and everything. And I'm saying this for you to understand the context we're going to study. And we see the vortices proliferating, and then suddenly we see vortices reacting. We don't watch each vortice reacting in reconnection with each other, but what we see is the identification of the vortices disappear, and the system became a big fluctuating cloud of amplitudes and probably phases, but we don't measure the phases. We measure the amplitude of the cloud. And then we start to characterize the cloud from that point on. And basically what we see is going from a few vortices to a very dramatic change of the density profile, which we characterize as the turbulent cloud, and we investigate. But we can keep going. If we keep exciting, after you believe you reach the turbulence and you keep exciting, we observe a very interesting phenomenon that is breaking down in grains of the condensate. And we never went to this part to study deeply, but we did a study I'm going to show to you using almost 1D to focus on the granulation. And this is a very nice effect. Okay, we characterize our sample. So we know more or less what we needed to excite, for how long we excite, with what amplitude to generate the turbulence. So this we spent a few years understanding, and with the help of some of the theoreticians like Tsubota, Yukalov, and Dubina, we've been simulating what we observe if it was reasonable for the interpretation we giving. So basically, combining the right excitation amplitude with the right time of excitation, we can conduct the sample to a turbulent regime. And then we try to stay in this region of turbulence and try to measure the main features that people normally associate with the turbulence, which is basically the power spectrum and some other characteristic features. And then from there, we go on for new studies. We have been simulating this, and I think due to the collaboration with people from Newcastle, they've been able to actually show that our turbulence is a little more complex than only vortices present. They've been showing that, during the excitation, or simulating very close to what we believe we're doing by introducing this potential misaligned with the axis and everything. We produce unstable solitons that break down in vortices and sound waves. And this goes in evolution to produce the turbulence. And of course, they've been simulating the cloud and showing the main features, which in some sense agrees with what we observe in the lab. Here, for instance, we see the experiment and the simulation of the cloud as should be after the evolution to turbulence and the projection, because we do an absorption, optical absorption of our sample. So we somehow project this 3D cloud in one single image in the 2D plane. Okay, and then this study has shown to us how the system of behavior, how those defects migrate into the sample, and how is the time evolution, and of course, how is the population, projected population of the particles in the momentum distribution. So this is the main quantity we measure in many of the experiments, is the momentum population, or the momentum distribution of all the particles in your sample. So we want to know how they are distributing the momentum space, and simulation and experiment somehow they have a lot in common, and then we believe that this is the correct things that's happened. We are producing this messy situation that takes the sample to turbulence. And of course, once we produce the turbulence, we're gonna go to characterize it. And we start to measure many things. And many of the things I'm going to do involve to obtain the momentum distribution, the momentum occupation, the N of K we call. And of course, we have to be sure we are measuring the right thing, and we do by time of flight. Time of flight means we destroy the potential and let the particles to fly. And by looking the expansion and how many atoms, what is the density you have in different regions of the expansion, you may reconstruct the momentum distribution. Of course, when you take the potential away, what you do is going to momentum space. So what you measure actually is the distribution of momentum. But we want to know the momentum distribution in situ. And if we have a strong interacting sample, we cannot rely on this technique, because what we'll be doing is measuring how many interaction is converted into momentum. So we had first to convince ourselves that we had a sample that was kinetic dominate, and we have done that with the help of a few good theoreticians like Fetter from Stanford, Gordon Bang from United States too, and some people in your group. And we have been showing that actually after all this transformation, all those defects being introduced and they react to each other, we have a sample that is kinetic dominate. So we are very much convinced that we can measure the momentum distribution using the time of flight. But you can also measure momentum distribution doing density-density correlation, and through the Fourier transform, get the power spectrum. And getting the power spectrum, this is a well-established technique to do the Wiener-Cincini kind of application, and then you get the energy distribution, the energy spectrum, right, of your sample. So we've been applied both for the momentum distribution in time of flight. As I told you, we do time of flight, the sample is expanding in 3D space. Nevertheless, we project by light absorption, and we observe the atoms distributed in the expansion, and it's still in the plane that we project. But by doing a Bell type of transformation, and with some considerations of symmetry, we recover the 3D momentum distribution, and we use that to see what we have. And then that's what I've been doing for many years, is measuring those momentum distributions, and from them obtain the 3D momentum distribution. On the left, you see the 2D, and then we do the transformation, we get the 3D, and it's clear to see in the right range of momentum, we see the appearance of a power law, which somehow is an indication, right? It's not the only indication, but it's a good indication that there is a cascade going on. You have a range of momentum, the inertial range, where particles or energy will flow from one side to the other. And we are now convinced by the end of the talk, you're going to see that we have a particle cascade, directly particle cascade, going from lower to higher momentum. Okay, so this is what we've been doing. If you want to know more about the power spectrum, we measure many things using the power spectrum, and basically with the power spectrum, it's nice because you can see the evolution of the momentum distribution in many different instances of time. And of course, they agree. We ask the question, when we get the energy spectrum by obtaining the momentum occupation distribution, and assuming that we have a kinetic dominate state, so multiply by chi square, you have the energy dependence with the momentum, which is the energy spectrum, or you can do the power spectrum type of measurement with the Fourier transform of the density-density correlation. And then we have to show that both agrees, and we have been showing that both agrees well. When you look into the exponent of the K in both cases, they all come closer to the -1, which is the expected for the type of turbulence. So we believe we have. Okay. Now, there is some questions about isotropy, because even during the expansion, our sample is not isotropic. And we're still understanding what is that about. But it's very interesting because the main features of the turbulence does not change in both directions, even though the sample is non-isotropic in expansion, the properties are isotropic. Only the ranges change a little bit, right? So if you see here, the range where we have the power law, it changes a little bit. But the same power law is obtained in any direction that you go and observe. We have measured, as you know, in the range where in the region of momentum where you have the power law, we believe that you have a flow of energy or particles. And then we've been trying to characterize that by measuring the time evolution of the moment of the energy spectrum. You can do a conservation equation, continuity equation in momentum space by having the source of energy or perturbation in the lower momentum part, and that will flow to higher momentum. And then you can work out the equations, and in the absence of injection, so you perturbate and you let the system evolve. So in the absence of injection of energy or dissipation, you can basically show that the flux is basically determined by the time variation of the integral of the energy spectrum. This is a well-known formula that people uses, and we've been using that to characterize as well what we observe. And this is typical time evolution of the energy spectrum we have, and by looking the time variation of the integral in different intervals, you can find the intervals where the flux is constant. There is no time variation of the flux, which is the characterization of the range where there is a flow without dissipation in this region. And that's how we've been finding out where is the inertial range. And it goes from one value, initial value, to a final value. It's not a long range because our sample is tiny and everything, but we've been characterizing as being consistent all the time. We also been evaluating the disorder, calculating a kind of entropy is equivalent to the channel type of entropy in your sample. And by looking the distribution and the fluctuations on the momentum space of our sample, we can come and calculate the entropy and evaluate how this entropy is evolving as we excite. And for sure, all the time, as we change the amplitude of excitation, fixing the time of excitation, we observe that the entropy start to shoot up whatever we detected the other properties, whatever we detected the development of turbulence. So also is a good indication that the disorder being installed and the turbulence is in place. And finally, as characterization, we've been measuring this integral scale length, which more or less tells us in what kind of scale size the energy is located. And this is done also by knowing the energy spectrum, and by integrating, we can find out what is this length. And as you can see, the length decays with the time. After you produce the turbulence, this length will decay, showing that the energy is actually flowing to small scales. And you can somehow map this, considering in a first approach that the length, this integrable length scale is an exponential type. You can find out how long time it takes for the decay. And of course, what is the amplitude that starts? And as you can see, the amplitude always starts in some value, because that's how you start. It does not matter what amplitude of excitation you've been using. You always start in the largest possible scale to introduce the energy, and then that scales decay down to lower value depending on the amplitude with the time. So the time until zero, this will depend. So the system will decay faster and faster depending how you use the amplitude. Well, for most of the things I'm going to show from now on, it would be very important to characterize how far from equilibrium you are. Therefore, we've been trying to devise an experimental technique to quantify how far from the original equilibrium situation we are. And there are many possibilities. One of them that we use, that we are not fully convinced yet, but we are working on it, is to take the cloud, and we know that in equilibrium, the cloud is a composition of a Thomas Fermi, plus a Gaussian profile, which is the condensate component and the thermal component. And then we try to see how much we deviate from that and how we build up this value of deviation from this equilibrium situation. And as you can see, at very lower amplitude of excitations, we normally affect very little the equilibrium, but when we reach situation where we believe the turbulence is stalled, or we measure that properties are changing, this quantity grows up. But we still kind of holding to quantify how distant from equilibrium we are. Now we have the non-equilibrium system. We have this turbulent. We did some characterization for a few years. Now we want to apply for something. And then we have either in expansion cloud. So we have this collection of matter waves in your sample with different amplitudes and phases and everything. And we want to see how that behavior. And one of the things is let this expand. And when that expands, of course, you all know that laser is for light, what condensate is for a thermal gas, right? Many particles in one mode, many photons in one mode, and so on. So we did that, and of course, this is equivalent. When you let a turbulent cloud to expand, this is a way to produce speckle of matter waves. And you know, there are many applications for speckle in light waves. Now, we believe that eventually can be applications of speckle of matter waves. But also, we can do this non-equilibrium and look for properties, including the presence of non-thermal fixed points, which are those points where the system hang around a little bit before start to progress the thermalization. And then in that case, it is an analogy or extension of the thermal fixed points in conventional phase transition, where the system hang around that is fully characterized by some universal function and some exponent, right? As we know from renormalization group theory and things like this. So we went for that, for trying to characterize this non-equilibrium stuff and the presence of universality. And there is also Anderson localization, which is something that's on the back of my mind, because I'm going to show you what I have in mind, even though we never published this, because we are still convincing ourselves. And because in this audience, there are so many good theoreticians, I think maybe some people got interested in help us to simulate it, the ideas. So for the speckle wave, you imagine the turbulent cloud expanding. It shows the interesting behavior that we detected from the very beginning, you know, the self-similar expansion and everything. And then that reminds us of the propagation of speckle of light field. Speckle of light field is this combination of random amplitudes and phases that start with a laser field scattering a random surface. And then that light has this very beautiful pattern and properties of propagation. And what we did is map or condensate into or condensating expansion, reminding the first Ketterle experiments on laser of atoms and things like this. But here is a random distribution of amplitude and phases. So it is actually like the speckle. And we have characterized that, showing that, you know, when you have a normal laser beam propagating, you all know that the diffraction or the divergence of the beam is done by the wavelength divided by the waist, the size of the beam. But when you have a speckle, each speckle behavior like a tiny laser. But as a whole, they behave like the wavelength divided by the correlation length. And therefore, the correlation length is much bigger. So this does not diverge as a normal coherent beam. And that's what we observe during the propagation. And we compare in the experiment what's happening with a BC in expansion and then with the optical beam expansion, which is very equivalent, of course. But then we made the comparison of, well, we calculated the second order correlation, density, and intensity correlation. And then we show that the light beam and the atomic cloud, either in speckle or non-speckle, is equivalent to this laser beam. So this is a very nice result, I think, a good application of a turbulent cloud starting in a trapped BEC. And I think this is a merging of quantum turbulence with statistical atom optics. As you know, atom optics is a field already established, but they don't do a lot of speckle, they don't do a lot of statistics in there. So maybe they could do, and this is a good example of speckle of matter waves in 3D, which was something mentioned in the literature many times to be produced back about 2 decades ago. Okay, now comes the most interesting part, a non-thermal state. When we produce the turbulence, you know, we know that the system is really cannot be in equilibrium, right? We see. But let's see how is the thermal part of it, which means the Gaussian tail. Normally, the Gaussian tail will tell us if this is a thermal state, if I can characterize by a temperature or not. And it turns out that the turbulent cloud of atoms, when we do the analysis, it behaves more like an exponential type of tail than a Gaussian type of tail. So we have here an example of non-thermal state, right? And we've been characterized this non-thermal state because if it is non-thermal, it was not born as a non-thermal, start with as a thermal state, and then we start to excite. So where it becomes a non-thermal state, and then we find that whatever it became turbulent from the previous characterization we have done, it also shows exponential tail. So the conventional Gaussian became exponential for that sample. And that the Gaussian, it is in expansion, but that is the way that we determine the temperature. That's the way we do the thermometry of the cloud, is by looking to the Gaussian part of the system, which is the thermal component. So this has no thermal component because it's exponential. And as I increase the amplitude, fixing everything else, I see that I go exciting, but whatever my non-equilibrium is well characterized, whatever the power law in the energy spectrum or in the momentum distribution appears, it became exponential. Well, just to clarify to you, we are not looking to the range where the potential, the power law appears. We are looking to the far momentum, the tiny little tail of the expansion, which is what we use to characterize the sample. And of course, this exponential developed, alpha here is the exponent. If it is 1, is exponential. If it is 2, is Gaussian. So we go from Gaussian to exponential, depending on many things. So as time of excitation, because you are inputting energy, so we have characterized fully this, based on the parameters that we know how to input. So if you increase the time of excitation, it comes faster. If you increase the amplitude, or I'm sorry, it will come, if you increase the amplitude, the exponential will come faster because you're putting more excitation, you're putting more topological defects in there. So this system will faster evolve to a non-thermal state. And we've been characterized in different ways, including the exponent, because this, when you put in expansion, this is R divided by some characteristic length. And we've been characterized everything. And of course, this depending on having a decent population in the condensate. If you have a very tiny condensate, we knew that almost nothing happens there. We already reported this. We could not develop a very nice turbulent cloud with a 20% condensate. We needed to reach higher population, higher fraction of the condensate to be able to reach the turbulence. Here too, we needed to have a decent fraction in the condensate to be able to reach the exponential type. And then I came with this crazy idea that what's happening is equivalent to Anderson localization with the matter wave. Of course, this is being very well studied, and Alain Aspect, that got Nobel Prize this year, also did some experiment on this field. And my idea is that I have this thermal cloud, is minimal amount of atoms, but then I have this turbulent cloud at the center, and they are all interacting each other, and the scattering of the thermal atoms by the turbulent cloud somehow produce a kind of localization of these matter waves. And I try to characterize that, and so far we did not reach a final verdict. That's why we never published this. But my idea is that the main field of the atoms in the condensate concerning to the thermal atoms work like a random potential for the scattering. And then we see a type of localization, which is sometimes characterized by the exponential type of behavior. Okay, but for sure we have a non-thermal state. And if you have a non-thermal state, why not looking for those non-thermal fixed points as the system try to thermalize? And this is, of course, non-thermal fixed points is you start with a system out of equilibrium in any condition you want. This will evolve, and it may or may not find conditions that make a kind of metastable. The system are hang around those points. That's why it's called fixed points, equivalent to the thermal fixed points in the traditional phase transition or so on, where the system are hang around those points. And around those points, people predict universality. They predicted that the evolution is well determined by a universal function that is fully characterized by two exponents, alpha and beta. And then the system may not hang around forever around this point. It may depart from this point and then goes to equilibration again. So this is actually in the past, I think this was called pre-thermalization type of phenomenon. And we try to detect this in the turbulent cloud. And we need to see the time evolution, right? And we need to see the time evolution of the momentum distribution we measure and see if that shows any evidence of well behavior scalability, because this is one of the prediction around a non-thermal fixed points. It's a collection of is a situation where somehow the system interacts in a way that it keeps around there evolving as by a basic law of scalability. So normally around those non-thermal fixed points, well, there are many people that have been studied these non-thermal fixed points either numerically or analytically, and they've been reaching very nice results. And as I said, there is an analogy of this renormalization theory that is done around the critical, is done for critical phenomena around the equilibrium points. And they predicted that around those points, correlation should evolve as a universal function f, depending only on two exponents, alpha and beta. Specifically for the momentum distribution, we should have the momentum distribution around those conditions evolve with a scaling of the amplitude, which is, this is evolution with time. So let's take T0 as a reference time. So the amplitude should scale as T over T0 to the alpha, and the momentum scale, which is the lens that you look, the system should evolve with the T over T0 to beta. And alpha and beta can be positive or negative depending on the direction of your flow. And it should characterize the system. And then if that's true, that is a universal behavior because you have a universal function with two exponents that predicts the time evolution of your system around those points. And people is been trying to find such points and such physics, quenching with the wave turbulence or with our turbulence that is not exactly wave turbulence. There are many people around those last years proposing to observe in different situations, almost all related to quench. So they always start with a thermocloud quench, and during the time evolution of this quench, they see this behavior that they can see if the momentum evolution and characterized by a universal scaling. So by doing the scaling, you make all the plots be the same. So this is the typical momentum distribution, time evolution we have. Here the colors, I hope you can see, are different holding time. So we produce the turbulence and then we take the excitation. And the system is now evolving alone, isolated, with whatever excitation we introduce on it. And they're evolving for different times. And as the system evolves, we observe the momentum distribution evolve as well. The idea is, let's see if we can find a range where this is characteristic of a scaling law and is characterized by a universal function with characterized universality. Okay, and of course, there are many requirements for being around non-fixed thermal points. One of them is should be independent of your initial state. So for us, if we excite with small amplitude or big amplitude, we should have the same stuff. A second thing is there is some range because we should preserve number and we should preserve other quantities in your system. We call these global quantities that should be preserved and evolve in such a way to characterize the non-thermal fixed points. So what we did is excite in different amplitudes. Here you can see different amplitudes that we excite and we see different evolutions. And of course, for each of those, we can go and scale each momentum distribution. They happen different times. And then we try to scale following this relation. We don't know exactly what is the function, but if it is universal, we can scale the momentum and scale the amplitude, and they should get one on the top of the other. And as you can see, that happens. And happens with a characteristic exponent, alpha, which is the amplitude exponent, and beta, which is the momentum scale scaling of alpha equal to minus 0.5, that is a deviation, of course, and beta equal to minus 0.2. And different states produce equivalent, the same exponents. And then we have being evaluate of all of this. You see that the amplitude normally is given by how much energy, amplitude, the energy we put in this potential, and normally is given by the chemical potential, how a few times the chemical potential of the ground state. And we realize that there is actually a range. It is predicted by the theory that you have a momentum cutoff above which there are many other things taking place, and then the scalability may not be there all the time. You may have an infrared, which means very high momentum here, or you may have a UV, which is short momentum here with different coefficients, right? Because of this, what I told you. And we've been investigating many different samples, and those are the global quantities that should be preserved. You can calculate the number of particles should almost be constant during this interval and during the time you are observing. and that's the top global variable number, which is the integral, in that range of momentum is about constant, small variation. And then there is a second quantity, which is this integral of the momentum, is the integral of the energy, is basically the integral of chi-square normalized, and that should scale with time following the beta coefficient. And of course, what you see in the bottom is the M2 of our sample within the range that we claim that we are seeing the non-local, the non-fixed thermal points, and the fitting with the beta that we find, and they fit quite well. And of course, since the number is constant on the first one, you should require the number constant, which means you should kill the time variation. And then there is a relation between alpha and beta in this situation, which is related by the dimension of your system. Alpha and beta should be the same signal, and they should be proportional by the number, which is the amplitude. So if you are in one dimension, D is 1. If you are in 2, 2, and 3. So that's the dimension of your system. So we've been characterizing many, many different experiments, and it's very clear that we see this universality behavior. What the universality class we are, I cannot answer. How the system got to this point, that's my question at the moment. Why the system is getting there always? We input all these excitations, as you can, I showed to you, we using, including the simulation of our collaborators in Newcastle. You can see that we are generating not only vortices, we are generating also solitons and everything, but doesn't matter. Once you produce in different situations, they evolve around that window of time and momentum. They evolving following that scalability and that universal function. We also would like to understand what's going on between here and there. There is any indication that the system is seeing that region of parameters where it should be a non-thermal fixed points. And if there is any indication on the way the system behavior that will have a thermal fixed points on the way. So those are open questions. Well, we, as I told in the very beginning, we normally project our system. And by projecting the system, we could ask, is that still preserved? Alpha and beta, the scalability is still preserved? And then we did, of course, a deep investigation on that to show, and using Abel transformation, considering that you have the scalability, considering that your momentum distribution is given by the expression that I just showed to you, and then you can get that even projecting the system, you have the same type of scalability behavior. So if you project the system, even being 3D to 2D, you still are able to decide about the presence of a non-thermal fixed points. But alpha and beta in this case will be slightly modified because of the projection, right? And of course, we were able to calculate that beta does not change from 3D to 1D. And alpha, this is in 2D, will be 2/3 of the alpha in 3D. And as you can see from our numbers, it's quite decent. And if we go from calculating the alpha 3D, which is 3/2 of the 2D we measure, we're gonna get 0.75 instead of 0.5. And beta will still be 0.2. And they'll be closely related by a factor of 3. Well, all the things I showed to you in this last part of the presentation is in this paper. And there we discuss many details and some of the future we would like to do. And then as a conclusion, we've been observed, I think, a universal behavior in this atomic superfluid driven far from equilibrium and in the state of turbulence. We would like to, our work help us to better understand. You see, because when you do that kind of study, it may help to understand the evolution of a turbulent state to a new thermal state, which is what we are now preparing to measure. we were able to increase the lifetime of our condensate to many seconds. And now we already started to produce turbulence and see the system at the end of the day recovering the condensate and the thermal clouds, rethermalize, and maybe passing through a non-thermal fixed point. And then we may be able to understand this evolution, what these non-thermal fixed points mean in this rethermalization of a system out of equilibrium. Okay, well, our results suggest merging the quantum turbulence regime in trapped atomic gas into a new class of phenomena, which is this dynamical universal. But this is being said by many people, you know, Schimmeyer, people from Cambridge did a very nice work and mention all the time that turbulent regime should be. There are even some papers coming out by the group of Vesbabics and other. Well, I don't have time, but eventually I would like to point out to you that in 1D we cannot have vortices, as you know, but we can have a granulation. We can go all the way through and excite enough the system that will break down and never recombines again, stays there forever. And we'll be showing this with a 1D condensate, where by modulation of the interaction, we produce a breakdown and they produce grains, and these grains cannot recombine. So they are like being washed by the thermal atoms, very tiny little thermal atoms around, but they stay for a long time, many, many seconds without reconstruct the condensate. So this is also a nice system to break down from equilibrium and see how those islands with probably random phase each other can somehow recombine to make it again the full system with a single condensate. Well, I was going to tell a little bit about spontaneous generation of turbulence, but I think I have said enough. And I appreciate your time and the opportunity for me to give an overall picture of what we're doing here in São Carlos, in Brazil. We have published a few papers that you may know, but if you are interested in our publication, we have a homepage with the full list of publication. And there is a special issue on the Quantum Science Journal, a journal that's held by the IAP, the American Institute of Physics, together with the American Vacuum Association, which is two institutions, two publishers, right? And they have a journal that's called Quantum Science, and there is a new issue coming up on non-equilibrium quantum system, and any of you that want to submit a paper, we'll be very happy to receive and to give a very nice consideration for your contribution. Well, thank you very much. And now I hope I can have a few minutes for you to ask me a few questions.
Thanks very much, Vanderlei, for a very interesting talk and a nice tour of recent results. It's actually one of the largest attendances that we've had at one of these webinars. So the questions that you're asking and addressing are obviously of interest to lots of people. So questions, feel free to either raise your hand or even just unmute yourself and ask a question directly, or if you're on a slightly dodgy internet connection, pop it on the chat and I can ask Vanderlei the question. While people warm up, I just wanted, it's obviously a very different system, but one of the analogies or analogous systems compared to your experiment will be something like galactic clusters, which are obviously on a very different scale, but you've got an extremely rarefied gas and turbulence driven by, well, different forms, but one of them is shock waves coming from galactic mergers and things like that. I appreciate you don't have shock waves here because they're traveling slower than the speed of sound, but they're still strong density perturbations. And so I wondered if you'd had any connections with people from this kind of astrophysics community to discuss this.
Yeah, we've been reading some of the papers where they do equivalent things. In fact, all this non-equilibrium stuff start with cosmology. I mean, started to trying to explain the universe as a whole, and we've been reading and good examples of things that we observe is being proposed by people in this field. Nevertheless, we don't have any connection yet with this community because we are starting to do measurement, and I'm trying to do very nice measurement under where we visit the non-equilibrium and come back, visit and come back to equilibrium and things like this, which somehow will create situation where you can go step by step, because I know that the system are complicated and give to the theoreticians a hard time, but that doesn't mean that's not interesting physics.
So, Nick.
Hi, Vanderlei. Very nice talk and loads of questions. Let me ask something. Some time ago, I remember in some of your papers talking about or mentioning informally the inverse Kibble-Zurek effect, as in somehow starting from something which is very condensed and then going backwards through the generation of vortices. Would you know, maybe it's a strange question, but is there any connection of that with these sort of going through non-thermal fixed points? Because you're somehow starting from some kind of well-defined state and you're generating something very highly excited, which I guess if there is some kind of inverse Kibble-Zurek, there would be some kind of scaling laws there, which I'm not sure how well known they are.
Yeah, well, you said right, Nick. We published a paper a few years ago saying that the inverse Zurich mechanism should exist instead of quenching through the condensate situation and see the evolution and see this kind of behavior. We say there that we could start with the condensate, perturb enough for the system to try to rethermalize, and we see equivalent behavior. So the answer is yes. I wrote a paper together with some people on the inverse Kibble-Zurek mechanism. But this is what we are trying to go now in the new generation of experiments, to really measure things more quantitatively and not only qualitatively, and with time resolution, right? Because as I said to you, that the system may reach a non-fixed thermal point. It seems that there are enough evidences already. The thing is, what's happened to the system when it starts in so many different situations that make it go to that region of evolution, that make it hang around to be scalable there. And I think that that's interesting. And so we have to kind of slice the time evolution to be able to see. I think then we be giving contribution to the understanding of the evolution of non-equilibrium quantum systems, because you are all worried about, okay, the system is in non-equilibrium, what's happened now? At the end of the day, what I have in my sample is not forever, right? The system is going to need the mechanism to re-thermalize. And we're starting to see features in your system that indicates very interesting factors. And we are preparing to put this in a paper. But there are points that do not change in time. There are points, maybe it's not any system that will have non-thermal fixed points, but you need to collect a few conditions for that to take place. And well, you know, I am an experimentalist. I have Lucas Madeira with me, which is a theoretician. And you know, I know that in this audience, there are a lot of, well, I see some experimentalists, but there are many theoreticians, and people like you could understand the system much better in a way that we experimentalists can measure. Because if we come up with a very strange theory, we can never really sample steps of the theory. So we can only say, well, the phenomena exists, but we don't know if your explanation is correct, because we can't really go through this.
Okay, thank you very much, Vanderlei.
Any further questions? while we wait, I'll advertise that we've got our final talk before Christmas next week on the 13th of December. And that's going to be given by Yutu Sano from Osaka City University, who's going to talk about emergent isotropy of wave turbulent cascade in the Gross-Pitaevsky equation. And that's at the slightly unusual time of 10 a.m. In the UK, just given the time difference between here and Japan. An email as well.
Andrew.
Yeah.
Andrew, sorry to interrupt. You could send it to us, please.
Yeah, I've added you to the mailing list.
Because you see, I see many members of my group that are interested in seeing, and we'll be very happy to see, even though the time may be confused, the time zone, but it's okay. We are very interested in the topic you mentioned. So
yeah, please just email. Well, I've popped you on the mailing list, Vanderlei, but anyone else here, please just email me. You can find my email on the. I'll pop it in the chat while we're here. So in the chat, you'll find the web page for the webinar series. You can find my email address or the other organizer's email address. Just email one of us. We can add you to the mailing list. If you're interested in giving a talk, obviously let us know. All past webinars have been recorded, and there's a link to a YouTube channel where we're building the sort of Netflix of quantum fluids. So there's, I don't know, 20 plus talks on there that might be of interest as well. But I've added you, Vanderlei, and I'll add anyone else from your group who gets in touch. So a final. Oh, sorry, go on.
Everybody can find my email. If you have any question or suggestion, please send it to us. We appreciate collaborations, suggestions, and we love to collaborate with around the world, especially with England. And I see Tsubota here, so we like a lot Japan, even though they are out of the cup. I'm sorry.
So one final call, speak now, or hold your peace. No, well, thank you all for attending, and hope to see many of you next Tuesday. Like I say, expect an email reminder to go out later in the week. Otherwise, have a very nice Christmas, and we hope to see you in the new year. Thanks. Bye, everyone.
Bye-bye.
Bye.